A Royal Air Force Harrier GR-9 attack jet, outgunned, outmatched, locked in a dogfight with an RAF Typhoon, one of the most lethal air superiority fighters on Earth. The Typhoon pilot had just simulated a kill on the Harrier's wingman and was lining up for the finish. The Harrier pilot needed to get his nose up to fire a sidewinder, but physics said no. The Bernoulli principle and the Harrier's wing design refused to cooperate. Then he reached for a lever most fighter pilots don't have. He yanked it back 40 degrees. The nose snapped up. The sidewinder symbology locked over the Typhoon. Simulated kill. What just happened was VIFF, vectoring in forward flight, a thrust vectoring maneuver practiced exclusively by Harrier jump jet pilots. It's been called a party trick, a gimmick, a tactical dead end. But the truth is different. You're about to see the 6 insane realities of VIFF that make it one of the most misunderstood and most dangerous capabilities in modern air combat. From its use in actual war to the moments it nearly killed the pilots who dared to push it to the edge. The Harrier VIFF system uses 4 nozzles mounted centrally on the fuselage that move together in one plane, capable of deflecting up to 98.5 degrees, with 81 degrees required just to hover. Unlike the F-22's multi-directional rear-mounted thrust vectoring, the Harrier's nozzles are all clustered at the center of the jet, and they can only rotate in a single axis. Pull the nozzle lever next to the throttle, and all 4 pivot in unison. Early tactical recommendations called for 20 degrees of nozzle for sustained turns and 60 degrees for instantaneous turns. 60 degrees, pilots noted, definitely got the nose moving. For a Harrier pilot in the cockpit, it starts simple. Take your hand off the throttle, grab the nozzle lever, pull it back. What happens next is immediate and violent. A positive rapid nose-up pitch change, instability rippling through the airframe, and the aircraft slowing down fast. One former Royal Air Force Harrier pilot described pushing the nozzles to forward deflection, 98.5 degrees, as a whole load of deceleration, and admitted that mastering large deflections resulted in more than one complete departure from controlled flight, like being thrown through space in an asymmetric washing machine. This isn't witchcraft like the F-22's multi-axis thrust vectoring. It's physics weaponized in a way no other Western fighter can replicate. And if a single lever pull can rotate your thrust vector nearly perpendicular to your flight path, you've just rewritten the geometry of the dogfight, even if only for a few seconds. VIFF has been used in real combat. During the Falklands War, a Sea Harrier pilot from 800 Naval Air Squadron deployed his nozzles mid-flight while attempting to get a sidewinder lock on an Argentine Pucara close support aircraft. He used the nozzles to slow his descent and improve his firing solution. The shot didn't connect, but the maneuver proved VIFF could be employed under fire in a war zone when survival depended on it. Imagine being that Sea Harrier pilot, descending fast, enemy aircraft in your sights, seconds to decide. You don't have time to think about aerodynamics or energy bleed. You reach for the nozzle lever because it's the only tool you have that might change the outcome. The fact that the technology even made it to the battlefield, when so many experimental systems never leave the test range, is itself a form of validation. VIFF isn't theoretical, it's combat proven. And while critics dismiss it as outdated, the reality is this. It was available in an aircraft that made it to the war zone and gave pilots an option other fighters couldn't offer. When you're alone over hostile territory, that option might be the difference between going home and not coming back. In dissimilar air combat maneuvering exercises, a former RAF Harrier GR-9 pilot recorded simulated successful shots against an F-15, against an RAF Typhoon, and from an FA-18E against an F-22. In all 3 cases, the poorer air-to-air combatant won. Against the Typhoon, the pilot used VIFF to achieve the kill. The pilot was clear. Does that mean that Harrier plus VIF was in any way comparable to the Typhoon in an air-to-air engagement? Of course not. Not by a country mile, well, closer to a light year. But VIF extended the Harrier's envelope just enough to create a lethal opportunity. Picture the Typhoon driver, confident, experienced, flying one of Europe's most advanced air superiority platforms. He's just simulated a kill on the Harrier's wingman. The remaining Harrier is an attack jet, not a dogfighter. This should be over. Then the Harrier's nose snaps up 40 degrees in defiance of its aerodynamic limits. Sidewinder tone. Simulated kill. The Typhoon pilot just learned that overconfidence against an unconventional capability can be lethal. VIFF doesn't make the Harrier a match foe.
VIFF doesn't make the Harrier a match for 4th or 5th generation fighters, but it proves that a single asymmetric advantage, used correctly, can change the outcome of an engagement. And in a real conflict, where every aircraft counts, turning a guaranteed loss into a Hail Mary win can shift the entire tactical picture. VIFF works by redirecting thrust, which provides a nose-up pitch change in exchange for massive energy loss. The Sea Harrier FA2 aircrew manual confirmed that dropping the nozzle produced a trim change, both from using thrust to counterweight the aircraft and from generating a moment between the thrust axis and the center of gravity. That relationship varies with nozzle deflection. The price for changing thrust direction is instability and deceleration. As one pilot put it, what you gain in instantaneous pitch, you pay for in reducing energy, and the maximum attainable G will reduce as the aircraft decelerates. VIFF is a one-shot deal. If you don't make it count, subsequent maneuvers won't go your way. For the pilot, the sensation is disorienting. You pull the nozzle lever. The nose pitches violently upward. The jet becomes unstable. Your speed bleeds off fast. If you miscalculate, if you VIF at the wrong moment, at the wrong angle, against the wrong threat, you've just turned yourself into a slow, unstable target. One pilot described large-angle VIFF attempts as resulting in complete departure from controlled flight, like being thrown through space in an asymmetric washing machine. VIFF is not a miracle weapon. It's a high-risk gamble. Used correctly, it can extend lethality and survivability. Used incorrectly, it creates the mother of all aerodynamic catastrophes. And in air combat, where margins are measured in fractions of seconds, one bad VIF can turn you from hunter to prey. VIF places abnormal stresses on parts of the aircraft never designed to handle them. The enduring limits on VIF weren't about the nozzles or the engine. They were due to the high pressure ducts running from the Harrier's Rolls-Royce Pegasus engine to the control vanes used for vertical/short takeoff and landing flight control. These ducts were pressurized when the nozzles deflected, and they could only withstand so much stress before catastrophic failure. Imagine being the engineer who discovered this during testing. You've just watched a pilot execute a flawless VIFF maneuver in combat trials. The tactic works. The concept is validated. Then you inspect the airframe and find stress fractures in ducts carrying superheated, high-pressure air from the engine. Ducts that, if they fail in flight, could cripple the aircraft's control systems or trigger an engine fire. You now have to tell the program office that the most exciting capability of the Harrier has to be limited. Not because the pilots can't handle it, but because the plumbing can't. Every revolutionary technology has hidden constraints. VIF's limits weren't tactical, they were structural. And that meant pilots had to master not just the maneuver, but the razor-thin margins between maximum performance and catastrophic failure. It's a reminder that in military aviation, the most dangerous enemy isn't always the one in front of you. Sometimes it's the engineering compromise behind you. The FA2 aircrew manual made repeated recommendations to keep VIFF simple until experience was gained. Pilots were taught nozzle biting, taking small chunks of deflection to gradually rotate the nose around the turn circle. This worked best when combined with off-boresight weapons capability. But the most extreme use of VIFF, forward nozzle at 98.5 degrees deflection was described as a whole load of deceleration, and a technique that, for one experienced pilot, resulted in multiple complete departures from controlled flight. His description: like being thrown through space in an asymmetric washing machine. You're in the cockpit. The enemy is closing. You've committed to a full deflection VIFF. The nozzles rotate forward. Your thrust vector inverts. The nose snaps up. But the aircraft doesn't follow a clean arc. Instead, the jet tumbles. The horizon spins. Your vestibular system screams conflicting signals. The stick feels disconnected from reality. You've just entered an uncontrolled departure, and you have seconds to recover before the jet departs so violently that ejection is the only option. This isn't a simulation. This happened to trained, experienced Harrier pilots who pushed VIFF to its edge. VIFF is not for the faint of heart. It demands absolute mastery, perfect timing, and an acceptance that one miscalculation can send you into an asymmetric tumble with no guarantee of recovery. But for pilots willing to ride that edge, VIF offers something no other Western fighter can provide: the ability to defy the predicted flight path, disrupt an attacker's tracking solution, and create a massive angle and closure. Tracking solution? And create a massive angle and closure problem that might be enough to evade destruction. It's a one hell of a ride capability. And for the pilots who mastered it, that ride might have been the only thing standing between them and a fireball. VIF, vectoring in forward flight, is thrust vector control practiced exclusively by Harrier pilots, using 4 centrally mounted nozzles capable of deflecting up to 98.5 degrees. It's been used in combat. It's achieved simulated kills against superior fighters like the Typhoon and F-15. And it sent pilots into uncontrolled departures that felt like being tumbled through an asymmetric washing machine. For fighter pilots, VIFF proves that asymmetric capabilities, used correctly, can extend your envelope just enough to turn a guaranteed loss into a lethal opportunity. But it's a one-shot deal, and if you don't make it count, physics will punish you. For air combat doctrine, the Harrier's VSIF demonstrates that unconventional maneuverability doesn't have to match the performance of dedicated air superiority platforms to be tactically relevant. It just has to create enough disruption to change the outcome. For military aviation, VF's structural limits, high pressure ducts that couldn't handle the stress, remind us that revolutionary capabilities are often constrained not by pilot skill or tactical utility, but by engineering compromises hidden deep in the airframe. But here's what no one talks about. As early as 1961, aerodynamicists were examining whether vectored thrust could unload the wing. At the same time, US Marine Corps pilots were experimenting with that natty little lever to see if an unloaded wing could be immediately reloaded for greater effect. That research didn't stop with the Harrier, because if thrust vectoring could give a 1960s-era jump jet the ability to disrupt 4th and 5th generation fighters, what could it do in the hands of 6th generation platforms with AI-assisted flight control, adaptive cycle engines, and neural interfaces that react faster than human thought? The washing machine might be about to get a lot faster,